Comets. They streak across the sky, sometimes barely noticeable, tiny dots of light. Other times, they explode into brilliance, tails stretching millions of kilometers, blazing across the heavens. But what makes some comets faint whispers, while others are cosmic showstoppers? The answer lies in size, composition, and how close they get to the Sun. In the next 13 minutes, we'll explore comet intensity levels, from the faintest icy wanderers to comets so bright they dominate the night sky. Ever wondered why some comets appear only once in a lifetime, while others return predictably every few decades? Or why do some comets break apart spectacularly, while others survive a close encounter with the Sun? Stay with me. By the end, you'll see comets not just as icy rocks, but as messengers from the outer solar system, carrying the secrets of planetary formation, water delivery, and perhaps even the origins of life itself. Level 0. At the very bottom, we find the faint comets. These are the quiet travelers, often just icy rocks drifting through the outer solar system, far from the Sun's warmth. Their nuclei are tiny, sometimes less than a kilometer across. Most are made of a mix of ice, dust, and rock, remnants of the early solar system. Because they are so far from the Sun, their surfaces remain frozen and inactive. They emit almost no gas or dust. They have no visible coma, no tail. From Earth, they are essentially invisible. Detecting them requires infrared telescopes or careful space-based observations. Yet faint comets are important. Even in their quiet state, they are time capsules, containing pristine material from the solar system's birth over 4.5 billion years ago. Every faint comet carries organic molecules, water ice, and dust grains that offer scientists clues about the early solar nebula. Think of them as cosmic wallflowers, drifting silently in the background, holding secrets billions of years old. Though faint, they are numerous. The Kuiper Belt and Oort cloud alone may host hundreds of billions of such comets. They are the sleeping giants of the solar system, quiet but fundamental to understanding our cosmic history. Level 1. Step up a notch, and we encounter the small active comets. These comets are larger or closer to the Sun, and their surfaces begin to sublimate, releasing gas and dust. This sublimation forms the beginnings of a coma, the hazy cloud surrounding the nucleus, and a faint, trailing tail. Typical nuclei range from 1 to 5 kilometers. As sunlight hits their icy surfaces, it heats pockets of ice, turning them into gas that carries dust particles away. This is why small active comets start to glow faintly as they approach the inner solar system. Comet 46P/Virtanen, during its 2018 close pass, was visible with binoculars, a tiny snowball, but one that stretched a tail faintly across the sky. Its activity was mild, but enough for observers to notice it against the starry background. It's like a tiny snowball waking up from a long nap, stretching its tail like a cosmic scarf. These small active comets teach us about perihelion effects, the changes in brightness and activity as a comet nears the Sun. Surface composition matters too. Comets rich in volatile ices, like CO or CO2, tend to activate sooner, while those with mostly water ice may stay dormant until closer approaches. Though they are small and relatively faint, they form the bridge between invisible comets and the spectacular comets that dominate the sky. They are subtle, but their presence matters. Every active comet we observe informs scientists about sublimation rates, tail formation, and nucleus composition. Level 2. Next, we reach the medium-intensity comets. These are comets that brighten noticeably as they approach perihelion. Their nuclei are larger, typically 5 to 10 kilometers across. Sublimation is vigorous enough to produce longer, more visible tails, sometimes stretching millions of kilometers. The dust tail reflects sunlight, while the ion tail interacts with the solar wind, creating a luminous, sometimes bifurcated structure. These are the comets that amateur astronomers can see clearly with small telescopes, or even the naked eye under dark skies. Comet Hale-Bopp, 1997. It captivated millions with its brilliance, visible for months in the night sky. Its tail stretched impressively, a striking demonstration of how size, proximity to the Sun, and composition interact to produce intensity. Now the comet isn't just passing by, it's putting on a show. Comet brightness depends on more than size. The rotation rate exposes fresh ice, creating jets of gas and dust that can change tail shape. Activity varies daily. Sometimes a comet brightens unexpectedly, surprising observers with an outburst of material. Medium-intensity comets also reveal solar system dynamics. Studying their motion, tail direction, and composition provides insight into solar wind, planetary influences, and the distribution of ice in the early solar system. They are active participants in the cosmic story, not just objects in passing. Level 3. Then we have the bright comets. These are large nuclei, often 10 to 20 kilometers in diameter, producing spectacular dust and ion tails. They can become visible to the naked eye over weeks or months, drawing crowds and inspiring awe. Example: Comet McNaught, 2007. It became so bright it was visible during daylight for a short time. Its tail stretched across the sky, a blazing trail of dust and gas. The comet demonstrated the maximum activity a medium-period comet can reach, producing thousands of tons of material per second. This is the comet that stops people on the streets, pointing phones at the sky, capturing a fleeting masterpiece. Bright comets also allow scientists to observe jet activity, tail morphology, and nucleus rotation. They are natural laboratories. Dust and gas ejected from these comets can intersect Earth's orbit, sometimes producing meteor showers. These comets appear once or twice per decade, making them rare and exciting. Observing them reveals not only their own properties, but also the environment of the inner solar system, from the solar wind to interplanetary dust. Level 4. Escalating further, we reach the giant or hyperactive comets. These comets can be 20 to 50 kilometers across. As they approach the Sun, their activity is extreme. Gas and dust production can reach 10,000 tons per second, creating enormous, bright tails. Hyperactive comets sometimes show multiple tails, intricate ion structures, and rapid changes in brightness. C/2014 UN271 Bernardinelli Bernstein, one of the largest comets detected, currently inactive in the outer solar system, but its sheer size makes it a future powerhouse as it approaches perihelion. These giants are cosmic freight trains, barreling through space with thousands of tons of material in their wake. Hyperactive comets are often fragmented or freshly exposed, explaining their extreme activity. Studying them provides clues about early solar system ice composition, surface layering, and the behavior of volatiles under intense solar heating. These comets are rare, and their observations are fleeting opportunities. When one becomes visible, it's a chance to see the raw power of a comet's nucleus interacting with the Sun. Level 5. Now we have the sun-grazing comets. These comets take death-defying dives extremely close to the Sun, sometimes within a few solar radii. The heat and tidal forces can strip their surfaces, fragment them, or even destroy them entirely. Sublimation is intense. Coma and tail become massive. Brightness can increase tenfold or more in hours. Comet Lovejoy, C/2011 W3. It survived perihelion, spectacularly bright, with a tail stretching far across the solar corona. Sun grazers are extreme. Either they survive, producing an awe-inspiring display, or they disintegrate in the Sun's fury. They dive headfirst into the Sun's furnace. Some survive, some don't, and every time we get front-row seats. Sun grazers teach us about thermal stress, solar radiation, and tidal disruption. They are natural experiments in extreme conditions, revealing how cometary material behaves under intense heat and gravity. Their debris can contribute to meteor showers months later, linking a single comet's journey to events on Earth. Level 6. Some comets leave a mark on history. These are the bright comets, the ones that stay in memory for decades or even centuries. Their nuclei are usually 10 to 50 kilometers across, large enough to produce tails stretching tens of millions of kilometers. As they approach the Sun, sublimation creates massive comae, often visible to the naked eye. Take Comet Ikeya-Seki, 1965, a sun-grazing comet that briefly outshone Venus. Its tail extended across a huge portion of the sky. People could see it even in daylight, a fiery streak above the horizon. Comet McNaught, 2007, was another such spectacle, dazzling the southern hemisphere with a brilliant tail. These are the comets that make people stop, look up, and take a moment to stare at the sky. Bright historical comets are rare. They give astronomers unique opportunities to study comet structure, tail dynamics, and solar wind interactions. They also provide insights into volatile materials inside the nucleus. Some may undergo outbursts, suddenly brightening for days, revealing fresh ice or fractured surfaces. Level 7. Not all comets survive their journeys intact. Some fragments, breaking into pieces due to tidal forces, thermal stress, or internal pressure. These fragments often become brighter than the original comet, creating multiple Comet tails. A famous example is Comet Shoemaker-Levy 9, which fragmented into dozens of pieces before colliding with Jupiter in 1994. Each fragment produced a fiery impact, leaving dark scars on Jupiter's atmosphere. On Earth, fragments from disintegrating comets can create meteor showers, linking these dramatic cosmic events to our skies. Fragmentation exposes fresh ice and volatile materials, often causing sudden outbursts. These events help astronomers study internal structures and compositions that are otherwise hidden in the nucleus. In some cases, fragmentation can produce hyperactive comet behavior, temporarily boosting brightness by a factor of 10 or more. Exploding or fragmenting comets are a vivid reminder that these icy travelers are dynamic and unpredictable. Their activity and evolution are influenced by internal stress, rotation, solar heating, and gravitational interactions, making each appearance unique. Level 8. Then we have the hyperbright comets, rare and magnificent. These are usually long-period or extremely massive comets originating from the Oort cloud. Their nuclei are often tens of kilometers wide, and when they approach the Sun, the energy released can produce a coma and tail brighter than magnitude -1, visible even during twilight. Comet Hale-Bopp 1997 is the archetype. Its nucleus, roughly 40 kilometers in diameter, produced an extraordinary dual tail, captivating skywatchers for months. Its sustained brightness made it one of the most observed comets of the 20th century. These are the comets everyone remembers, the ones that turn a quiet night sky into a cosmic stage. Hyperbright comets provide critical scientific insights. Observing their tails helps study solar wind interactions, dust particle dynamics, and gas composition. Their brightness and longevity make them ideal for detailed spectroscopic observations, allowing us to measure volatile compounds like water, carbon monoxide, and ammonia. These comets are rare, sometimes appearing once in a generation. Their brilliance is fleeting, yet their contribution to science and public imagination is profound. Level 9. Occasionally, comets arrive from beyond our solar system. These are the interstellar comets, rare visitors traveling on hyperbolic trajectories that indicate an origin outside the Sun's gravitational influence. Two notable examples, Oumuamua 2017 and 2I/Borisov 2019. Oumuamua appeared as a fast-moving cigar-shaped object, while Borisov resembled a more traditional icy comet. Both were monitored intensively, offering scientists a first glimpse of material formed around other stars. They're cosmic tourists, passing through our solar system at incredible speeds, leaving only a fleeting glimpse of their distant origins. Interstellar comets are important because they carry chemical signatures of other planetary systems. Studying them reveals the diversity of cometary materials, the presence of ices and organics, and even hints about planet formation in other star systems. Their brightness varies depending on size, composition, and solar distance. But even faint interstellar comets provide invaluable scientific data. Unlike local comets, interstellar comets rarely return. Their hyperbolic trajectories ensure a single visit, making each observation a once-in-a-lifetime opportunity for astronomers. Level 10. Finally, the legendary sight comets. These are the rare giants, the ones that dominate the night sky, etching themselves into human memory. These comets have large nuclei, often tens of kilometers wide, and as they approach perihelion, their coma and tails can span the sky, sometimes visible in daylight. Brightness can exceed magnitude -2, creating a spectacular visual display. Examples include Halley's Comet, visible to the naked eye during its 1986 and 1910 apparitions, and the Great Comet of 1811, which remained visible for nearly a year. These comets are the ones that inspire folklore, scientific observation, and awe alike. These are the comets that stop people in their tracks, pointing skyward and whispering stories billions of years old. Level 10 comets are not just showpieces, they are laboratories in motion. Their tails carry dust and gas that can intersect Earth's orbit, sometimes generating spectacular meteor showers. Their comet reveal composition, rotation, and activity patterns, allowing scientists to study solar system dynamics in exquisite detail. These comets are the grand finales of cometary intensity. They combine size, brightness, activity, and historical significance. Their appearance is rare, often once per century or longer, making each sighting a cosmic event remembered for generations. From the faintest icy wanderers to the legendary skyfillers, comets are messengers from the outer solar system. They carry secrets about the solar system's birth, the origins of water on Earth, and the building blocks of life. Some drift silently, barely noticeable. Others blaze across the heavens, tails stretching millions of kilometers. Every streak of light is a story, a frozen traveler with a fiery tail, reminding us that the cosmos is alive, dynamic, and full of wonder.